Hello and welcome to Vodcast 6.1. In this Vodcast, I will provide a very general overview of earthquakes. Let's start off by defining what an earthquake is. An earthquake is the sudden movement of one block of rock slipping past another along what we call a fault. Now, a fault is a fracture in Earth's crust. Put simply, think of it as a crack. Now, due to the intense pressure caused by rocks above, most faults will be locked until there's a sudden slip. But when those sudden slips occur, we have an earthquake. During an earthquake, seismic waves will radiate out from the focus, which is also known as the hypocenter. And the focus is the exact location inside of Earth where the slip occurred. Now, if we locate the point on Earth's surface directly above the focus, we call that point the epicenter. So just to recap, the hypocenter is the exact location inside of Earth where the earthquake originates, and the epicenter is the point on Earth's surface that is directly above the hypocenter. Let's try to develop a conceptual understanding of the earthquake mechanism. Shown in the center image is a 4-step look at the earthquake process. And to help you conceptualize this process, for each step, we want to think of bending a stick. And we're going to bend that stick to its breaking point and then beyond. In part A, we're just looking at a pre-existing fault. The red line indicates the fracture in Earth's crust. And to the left side of the fault and the right side of the fault, we see the original positions for the rocks. So to start our conceptual understanding, just imagine holding the stick with both of your hands. Now let's focus on image B. And it's important to note that this process occurs slowly. We're talking about timescales of tens or even hundreds of years. If we're looking at a transform plate boundary, you see that the plate on the left wants to move in the northern direction, and the plate on the right wants to move in the southern direction. So along that fault line, the rocks on each side are grinding against each other. And as they do so, the rocks will bend and start to store elastic energy. So for our conceptual understanding, now imagine starting to bend that stick. And there's elastic energy stored in the stick as you force it to bend out of its natural position. Okay, now let's turn our attention to image C. This is where the earthquake occurs. At some point, the frictional force just can't keep these rocks from slipping past one another. And as soon as that slippage occurs on that fault line, we have an earthquake. For our conceptual understanding, you kept bending and bending that stick more and more until it reached its breaking point. And then once the stick snaps, you release all that elastic energy. You'll probably feel each of the pieces vibrating in your hands. And what you're essentially feeling is the energy released from that breakage. Well, if you were standing in this region that experienced the earthquake, you would probably feel that energy too. And then in part D, we see that the earthquake is now over. The rocks have returned to their original shape and they are now in a new location. With that stick in your hand, right after you snapped it and it stopped vibrating, now you just have two pieces of stick. And you can kind of think of that as the breakage being over. Well, in part D, the earthquake is now over. What we were looking at in these four images was a transform plate boundary. If you compare the stream shown in picture A and in picture D, we see that the earthquake has produced an offset stream channel. And we often find offset stream channels on transform plate boundaries. And one other point I'd like to make that's very important to note is that in part D, what we had was elastic rebound. And elastic rebound is when rocks snap back to their original stress-free form right after an earthquake. So where do most earthquakes typically occur? The two primary plate boundaries that most earthquakes will occur at are transform plate boundaries and convergent plate boundaries. Our first consideration is earthquakes occurring along transform faults, as shown in this image of the San Andreas Fault. Recall that at transform plate boundaries, the plates are sliding horizontally past one another. The San Andreas Fault is an excellent example of a transform fault, and transform faults can produce both small and big earthquakes. Now, the most powerful earthquakes will occur at convergent plate boundaries. Remember, at convergent plate boundaries, we are seeing subduction occurring. And with that subduction process often comes what's called a megathrust fault. Megathrust faults will form as the subducting plate interacts with the overriding plate. And when there's slippage along those faults, some of the most powerful earthquakes on the planet can be produced. Let's take a real quick look at the worldwide distribution of earthquake regions. I'd like to first call your attention to the Circum-Pacific Belt, where about 95% of earthquakes will occur at convergent boundaries. At these convergent boundaries, those megathrust faults can be generated, and that's where you can see some extremely powerful earthquakes. Another thing to note about the Circum-Pacific Belt is that this region is also known as the Ring of Fire, because we see a lot of volcanic activity in this very same region. So I think conceptually speaking, it's important that you understand at convergent plate boundaries involving continental plates and oceanic plates, we often see volcanic activity and mountain building, while we will also see some extremely powerful earthquakes generated in these regions. Another region I'd like to call your attention to is the Alpine Himalayan belt, which runs through the southern portion of Asia and Europe. Earthquakes in the Alpine Himalayan region will be caused by continental plate collisions. And then one last consideration on this image is that earthquakes can occur at divergent plate boundaries. And if you look at the lines of earthquake regions in the ocean, you see that earthquakes can occur along ocean ridges. However, it's important to note that these earthquakes are generally very weak. How do we describe, measure, and quantify the power of earthquakes? It's very important that you know the difference between magnitude and intensity. Let's start off by talking about intensity, which is a more qualitative description of earthquake strength. Intensity measures the amount of ground shaking based on property damage. And put as simply as possible, intensity is a rough measure of local shaking. Take a look at the modified Mercalli intensity scale at the center of this slide. The scale goes from Roman numeral 1 to Roman numeral 12, where Roman numeral 12 is the highest amount of ground shaking possible, and Roman numeral 1 is the least amount of ground shaking possible. For an earthquake that has a Mercalli intensity of 1, you'd barely even be able to feel the earthquake, if you could feel it at all. But if you go to the other side of the table at Roman numeral 12, you would experience total damage. You'd actually be able to see waves forming on the ground surfaces that almost look like ocean waves. And you would see objects literally thrown up into the air. The other important concept on this slide is magnitude. And magnitude is a quantitative measure of energy released by an earthquake. You've probably heard of the Richter scale, and the Richter scale was a magnitude measurement scale. However, the Richter scale is outdated and obsolete because the Richter scale was kind of limited in its ability to describe really powerful earthquakes. We now use what's called the moment magnitude scale when we quantify earthquake magnitude. As shown on this image, the scale can run from 2 up to 9, and the strongest earthquake ever recorded measured a 9.5 on this scale, and that was the 1960 Chile earthquake. So when we talk earthquake magnitude, we're talking about the energy released by the earthquake. And for the moment magnitude scale, we're talking about the equivalent energy released by kilograms of explosives. So for instance, if you have an earthquake that has a moment magnitude somewhere around 2 or 3, the energy released by that earthquake will be equivalent to about 1,800 kilograms of explosives. Now, if we wanted to describe that earthquake, it would actually be considered a very minor earthquake. You probably wouldn't feel this earthquake, and this earthquake would not cause any property damage. But as we work our way up the scale, from say 2 to 3, or 3 to 4, or 4 to 5, we see a 32-fold increase in energy released in between each number. Our last consideration in this podcast are 2 specific examples of earthquake destruction. The first example I'd like to talk about is something known as liquefaction. Liquefaction is the phenomenon of transforming somewhat stable soil into mobile material that's capable of rising towards Earth's surface. In other words, liquefaction allows stable soil to act almost as a liquid during an earthquake. In the center image, we see what can happen when liquefaction occurs during an earthquake. Before the earthquake, we have stable soil. But during an earthquake, the shaking will destabilize the soil by increasing the space in between the grains. And when that destabilization occurs, the soil will act less like a solid and more like a liquid. Very obviously, if the soil is acting like a liquid, that's bad news for the building standing atop the soil. And liquefaction can often cause significant building damage during earthquakes. Another result of earthquakes that can cause massive destruction is what's known as a tsunami. Tsunamis are rapidly moving ocean waves that are generated by earthquakes that are capable of inflicting heavy damages, especially in your coastal regions. Tsunamis are often triggered by underwater earthquakes, and that earthquake will generate that rapidly moving ocean wave that we just talked about. The image shown on the right is from the Japan tsunami of 2011, and that tsunami caused catastrophic damage to the island of Japan. Okay, that concludes this podcast. This video served as a general overview of earthquakes, and in the 2 videos that follow, we'll consider seismic waves and Earth's interior.